Next is the long-term deflection in the cracked numbers. This long-term deflection is the very complicated one, and it's a very complex to determine the long-term deflection of the cracked number. So here, the prediction of the time-dependent deflections in the case of the long-term deflection for the cracked number due to the flexural stresses. According to Nebulian, there is no exact solution for the nonlinear integration, nonlinear cracker section, and it is an integral equations for which there is no closed solutions or there is no such solutions are available for the long-term deflection of the crack section. Here there is a numerical solutions has been developed in the tensile concrete zone on the strain distribution of the section, which has been considerably there is an effect in the deflections. So according to British Standards Code recommendations, it has been comprised of in which there is an use of the curvature of the cracker section, in which the effect of the shrinkage and the creep for the long-term deflection effect is been considered. So in this, the American Concrete Institute they use this in very simpler approach. In this additional long-term deflection resulting from the creep and shrinkage of the fracture member by multiplying the immediate deflection caused by the sustainable load considered by the factor. So that is given by lambda is equal to eta divided by 1 plus 50 P naught. Where P naught is equal to ES naught divided by BD, where ES naught is the area of the compression reinforcement, B and D is the breadth and depth of the section, where eta is the time dependent factor of the following values. For the 5 or more, eta value you should take it as 2, and for the 12 months you have to take it for 1.4, and 6 months you have to take it for 1.2, and 3 months for 1. So this is about the long-term deflection. Next we will go for the problem. Here the pre-stressed concrete beam having a cross section of a cross-sectional area A of 500 into 10 to the power of 4 mm to the power square is simply supported over a span of 10 meter. It supports a uniformly distributed imposed load of 3 kN per meter. So half of which is a non-permanent. The tendons follows a trapezoid profile with an eccentricity of 100 mm within the middle third of the span, in the various linear from the third span point to the 0 at the supports. The area of the tendon AP, area of the tendon that is AP is 350 mm square, have an effective pressure of 1290 Newton per mm square immediately after the transfer. So here you have to find out the short-term deflection and long-term deflection. The moment of inertia they are given, Young's modulus, and area and Young's modulus of the steel and concrete both they are given. So density of the concrete you have to take it as 23.6 kilonewton per meter cube. Creep you have to take it as 2. Concrete shrinkage you have to take it as 450 into 10 to the power of -6. Relaxation of the steel is 10%. So initially what is that? The stress is given. The stress is 1200 Newton per 1290 Newton per mm square. So load is equal to here load is equal to stress into area. See here the load it is given, the stress it is given here. Apart from that, the area it is given as 350. So 350 mm to power of mm square they are given. So what you have to do is the load load versus load is equal to the stress into area. You have to take it, so that is equal to, you will get so this is what the here you can see here the what is this is the stress they are given, this is the area they have given, so you multiple these two, so stress into area is equal to load is equal to stress into area. Okay, so stress, you have to calculate the multiple these two and you find out the area. Okay, so after finding the area, that's what here here you can see here 350 into 1219 into 350, if you multiple, so you got the value of 4,51,500 Newton. So later the load, so what you have to take it, the sulfate of the beam you have to calculate. So sulfate, so load it is given, they are given 5 into 10 to power of 4 they have given, so that one you have to take it and into multiple by the density, so finally you will get the sulfate of the beam. So otherwise what you do is you take the area of the section, area into density you take it, so finally you will get the sulfate of the beam. Either way you can do it. Okay, so next non-permanent load they are given in the question, that is 1.5 kilonewton per meter. So that is given in the question only, you can take it directly. So after that, so there is a permanent load of the dead load as well as the sustainable live load, so that is you add these two. Okay, so finally permanent load will be 2.6 kilonewton per meter. Okay, next you will find out the deflection due to the prestressing force. Okay, so they are given the trapezoidal section, the tendons which is being placed in the as a trapezoidal section. So here important is L1 and L2 is the two important one. So first you find out the L1 and L2. So L1 it is they given as 1/3 and L2 they are given as 2/3. So that's why what you do is one is 3.33 and L2 is 1.66. Okay, so 1/3 is 1.66 and 2/3 is 3.33. Okay, thrice of it. Okay, that's all. So it is 2/3, whatever the length is there, you just this multiple by 2/3, you do this, you will get this answer. Okay, so this multiple by this multiple by 2 times you do it, you will get this one. Okay, later, so eccentricity is given as 100. So by taking L1 and L2, so what you do is and E value 100, you find out the deflection due to the prestressing force. Okay, so here, so you use this formula, AP is equal to minus P by PE divided by 6E into 2L1 square plus 6L1 into L2 plus 3L2 square. So here L1 and L2 value you insert it, and finally AP will be minus 31 mm to power 31 mm upward. So minus you got the value, so that's why it is upward direction, deflection is upward. Next, deflection due to the non-permanent load, that is a live load. It is given in the question. The non-permanent load as 1.5 kilonewton per mm square. So deflection due to the non-permanent load is equal to 5W L square divided by 384 EI. So W here it is live load. Okay, so that's why it is written as Q. Okay, here, so it is written as Q. Here it is written as Q. Okay, so that's what you have to take it. So insert the value of Q as 1.5. okay, next L as 10 meter. E and I value both it is given here. Okay. So insert the value, then after substituting the value, the deflection due to the non-permanent load, due to the live load, you got 12.8 mm the downward deflection. Okay. So next is the deflection due to the permanent load. So G, the whatever the load we have been calculated that as a 2.68, that load you have to take it. So here the same equation you have to use it here also, but instead of Q here you have to use it G value of 2 point here 2.68. okay. That's what you have to use it here. Yeah, so here 5 L to the power of 4 384 EI you got. So G value 2.68 whatever you have been calculated here, so that one you insert here. Okay, 2.68 length you have been substituted as 10 meter. So EI, so it is given in the question, E is 334 into 10 to the power of 3 and I value is 4.5 into 10 to the power of 8. Finally, deflection due to the permanent load is 22.8 mm in the downward direction. So this is what the deflection due to the permanent load. So later, so after the calculating the deflection due to the due to the non-permanent load, next one you have to find out the short-term deflection. So short-term deflection due to the non-permanent load, whatever the deflection you have been found out, minus 31 plus 12.8 and 28.8 all together added, so you got the deflection as 4.6 mm in the downward direction. Next, in the non-permanent, you have to take only the two deflection. So if you see here, you have to take this one and this one. So they take these two and find out the deflection as 8.2 mm in the upward direction. So next, the long-term deflection. So in this long-term deflection, so this is P by I value, sorry, P by E value. So E, sorry, 1 minute, this one. So this is P by A plus P E divided by I value. Okay. So this is the formula which is being used. You have to use it. P load as which we have calculated, that one as 4,51,500. So area value, that one is 500, 5 into 10 to the power of 4. So P whatever we have put it here, the same value, write it as it is. Okay. Same value you have to write it. E value is 100, same write twice. So I value, it is being given in the question only, so write it as 4.5 into 10 to the power of 8. Okay. Finally, long-term for term deflection, for finding for that the stress is 19 Newton per mm square. So after finding this, so modular ratio you have to find it. So modular ratio is equal to Young's modulus of the steel divided by Young's modulus of the concrete. So that is Young's modulus of the steel is 200 and concrete is 34. Finally, modular ratio will get it as 5.88. So loss due to the relaxation is the 10%. So 10%, the maximum stress is 1290. 10%, that is the 129 Newton per mm square. So next is loss due to the shrinkage. So that you have to take the value of concrete shrinkage value. It is given in the question, that is 45 into 10 to the power of 6 and the Young's modulus of the steel you have to take it, that is 200 into 10 to the power of 3. Okay. So finally loss due to the shrinkage is 90 Newton per mm square. Okay, so next, loss due to the creep. So creep value they are given as 2, you have to take it. So here, apart from that, the value which you have given, so the deflection value, whatever you have been found out, so that you have to take it, and 5.8, that as 5.88 and 19. Finally, the loss of the creep, which I taught in the previous classes, you note down once. So that is 223 Newton per mm square. Finally, you add all these losses. So finally, you will get it around the 442 Newton per mm square. So initial force, it is been we calculated, that is 4,51,000. So the loss in the pre-stressing force is, so what you have to do is, so you have to multiply with the area with that. Okay, so finally you will get the change in the loss of the pre-stress. So that is 1,54,700 you will get it. Okay, so what is the change? So initial to the change in the pre-stress, so that is 4,50,000 51,000 to 1,54,700. So difference you will get around 2,96,800. So average pre-stressing force, you have to take this one, and the initial force is 4,51,000. So both you to take it, and average pre-stress force you take it, you will get 3,74,000. Okay, so next, long-term deflection is deflection due to the initial pre-stressing force and deflection due to the loss due to the pre-stressing force. Both you have to take it. So with the deflection due to the average pre-stressing force, these three you have to take it. Okay, for the long-term deflection. Okay, so that is the third one, the whatever the here third one. Yeah, the third one, deflection due to the average pre-stressing force due to the creep with the phi value, that is creep is 2, so that you have to multiple with the 2. So finally 31 minus 1,54,700 into 31 divided by 4,51,500 plus, so that 3,74,150 into 31 divided by 4,51 into 4,51,500, that has to multiple with the creep value of 2. Okay, so finally at the upward deflection is 72 mm, you will get it. So next is for the long term deflection. So long term deflection, so long term deflection is equal to 1 plus phi into short term deflection. So in this phi value, the creep value they are given as 2. So short term deflection you have been determined the earlier, that is 22.8. so that value only we have been used. So previously we have determined in the previous step we have been determined. So deflection due to the permanent load and non-permanent. In the permanent load we got 22.8, so that value you used. So by using that you will get the long-term deflection as 68.4. Okay, so in the long-term deflection due to the non-permanent load, that is deflection is 12.8. so in this long-term deflection, so after taking that value, that deflection as 12.8 in the downward direction, the total deflection here is one is 72, which we have been determined earlier, and 68 point, which is previously we have determined from the permanent load, and 12 point load, it is the long-term deflection due to the non-permanent load, that is 12.8. so altogether you add it, so if you make sum you get 9.2 mm deflection in the downward direction. Okay, so this is for the non-permanent load which has been acting. So that is the mid section. Okay, so that is for the downward deflection. So after this, see, finally there is a one small step is there here. See, when the non-permanent load is not acting. So earlier it is a when the non-permanent load is acting. This is the second case when the non-permanent load is not acting. In this, you have to take the deflection of the due to the self weight. That is deflection due to the long-term deflection due to the pre-stress. Due to the pre-stress, whatever the deflection you will get it, that is 72. So and 68. So long-term deflection due to the permanent load. So you have to take consideration of one is pre-stress, another is due to the permanent load. Okay. So when it is not acting, so you have to take that two loads. So you should not consider the deflection due to the non-permanent load. Permanent load case only you have to take it. So here when the non-permanent load is not acting, only so non-permanent load is not acting means you have to take consideration of permanent load which is acting. Okay. So permanent load which is acting, long-term deflection is 68.4 and 72 is the long-term deflection due to the pre-stress. So both these two values you have to take it. Finally, when the for the non-permanent load when it is not acting, the deflection is minus 3.6 mm in the upward direction. So that's complete this model.